All right. Good afternoon to everybody who is in the US right now. Good evening for those who are in Brazil. The Brazilian Statistics Association, thank you guys very much for all the efforts of being online at this point. We know things are a little bit rough. And most of all, I would like to thank very much Professor Tibshirani, who accepted to be with us today. So Professor Tibshirani is at Stanford University. He's going to talk to us a little bit about statistics and data science and applications to the COVID-19 pandemic that we are having at this point. What I would like to remind you guys is that Professor Tibshirani is actually a reference for us, literally, at the University of Campinas. We have several courses that are running on material that he at least co-authored. So just things like the generalized additive models. We have the statistical learning bits, and more recently, the introduction to statistical learning. Many of you, and actually I need to make this very clear, we have been having very good audience, but this is the first time that we are beating the 200 registered attendance on this web conference. And I'm pretty sure it's not because of me, it's actually all due to Professor Tibshirani. Thank you very much, Professor. And just as a quick note, I would like to let you guys know in advance, just to be aware a little bit on the announcements that the Brazilian Statistics Association will make, because in the next few weeks, we have some names already confirmed, but I do still need to work on the dates. So what we are gonna have soon, Sean, oh, there is a typo there. We are gonna have soon Sean Davis from the National Institutes of Health, David Schlesinger from Mandalix here in Brazil, Carolina Heitman from Federal University of Pará, Rafael Irizarry from Harvard University. And in addition, we have confirmation from Wanderson Oliveira, our epidemiologist who was in the team of COVID-19 at the Ministry of Health. So Professor Tibshirani, thank you very much for accepting our invitation. It's up to you now. What we agreed, guys, by the way, is that he's gonna present the first part of his talk. Then we're gonna get questions. And on the second part, he runs the second part, and then we're gonna have questions again. So, and he's gonna be very happy to answer questions. Professor Tibshirani was actually the one who gave the most beautiful short lecture that I had in Bootstrap about 15 years ago. Thank you very much, Professor.
Okay, well, thank you very much for the invitation, and hello to everyone. I hope you're staying healthy in this crazy time in the world. It's stressful for everyone, but hopefully we will all get through this. So I'm gonna, are you seeing my screen or?
Not yet.
Not yet, okay. I guess I should share it, okay. So, now, yeah?
Yes, yes.
Okay, so what I have here is, whoops. I have so this is a modified version of the talk that I gave to a data science conference at the JSM actually about 2 months ago. So it's actually, and I'll give you the slides for this talk. It's probably about an hour-long talk, but I'm not going to cover all of it. Basically, this is the outline, and the first part is sort of general comments about data science and health and supervised learning and sparsity, deep learning, general advice. So these first three I will cover. That'll probably take around 15 minutes. And then you want to hear about COVID-19. So I'm going to skip this, which is interesting, but will be in the slides. And I'll just do the last part, which is the Delphi project, which is a project I'm actively involved in COVID-19 forecasting. So we'll see. So we'll do this first general section, then I'll stop for questions, and then we'll go to the last section, and then we'll have questions after that. And I'm guessing it'll be around 30 minutes, the whole thing, maybe a little longer. I'm not in a huge rush if you're not. So, okay. So some general comments. So as sure you know, there's a lot of excitement about data science and health. Artificial intelligence, predictive analytics, precision medicine, they're all hot areas. There's a lot of potential. Around the Bay Area in Stanford in California, there's a lot of work going on at Stanford and companies trying to collect data about health and figure out how to use it to improve public health. And we've got, of course, a lot of data available in the Bay Area, especially, and also in East Coast of the US. There's a lot of technology that's been introduced to help in this effort. New machines and assays, smartphones, smartwatches, everyone's collecting data, and health is, even before COVID-19, health was a very big focus for data science, and now even more so. And there's been some good successes already in pathology, radiology, and other diagnostic specialties, right? So, and this is something she's surely seen, and I know Hal Varian, I've met him recently. This was very nice, he said this in 2009 about us statisticians, and then it was repeated a little years later by Harvard Business Review. So I mean, it's really true that being a statistician, maybe not called a data scientist, is really a very attractive job. And that's good for our students who are graduating. There's lots of opportunities to work. In the old days, you'd end up in a university or maybe a drug company. Now, everybody wants a data scientist, right? Everyone is making data, creating data. Startup companies, Facebook, of course, Google. So companies small and big are all collecting data and want to figure out ways of making sense of it. And the data scientist is a key person for that. Now, I remember when I was, a statistician many years ago, if I was at a party and someone said, so what do you do? And I said, I'm a statistician, they would run for the door, right? I mean, who wants to talk to a boring statistician? Now you tell them you're a data scientist. Oh, interesting, right? And so now all of a sudden our profiles are much more attractive. Now, what makes the problem challenging? Data siloing is a problem, especially in the US healthcare system. I don't know about Brazil, you can tell me later. One problem we have is to try to share data is difficult, right? It's hard to get data on to a given cancer with many cases, and sharing data in a very complicated medical system like the American one is difficult due to legal reasons, for example. In other places like Canada, where I'm from actually, Scandinavia, it's much easier to share data because it's all centralized, it's universal healthcare systems. So depending on what country you're in, trying to share data and get good access to good amounts of data is difficult in the health area. Another problem in health is that the bar is higher, right? It's one thing if you have a system to recommend movies and it makes a mistake, right? It tells you a movie you would have liked is bad or vice versa. In health, of course, there's a lot more at stake, right? If your system recommends a treatment for someone, that treatment kills the person, or something like that, that's clearly a very costly error. So you have to be more careful on health. And it's also true that the public is not very tolerant of errors that are made by machines. For example, you probably see with self-driving cars, the safety record is amazing, right? Like the Google cars, I think, have had maybe one accident in billions of miles, right? But when they have an accident, you hear about it. Meanwhile, humans like us are making mistakes every day when driving. But the sociology of it is the public is not tolerant of when machines or computers make mistakes, whereas it's expected that humans make mistakes. So all these things make it challenging to work in this area. Some high-level comments about data science and statistics. And this is sort of a culture evolution that I'm seeing happening. I want to make the point that data science and statistics is much more than just running a machine learning algorithm on data, right? And I think some data scientists, that's what they think of statistics as. That basically we take our data, we find our favorite machine learning algorithm, and we put it through the algorithm. Well, hopefully that's not the case. That statistics, especially, and data science in general, is a much more challenging and broad endeavor. For example, what is the question of interest? How can I collect data or run experiments to address this question, right? If you just take your data and run it through an algorithm, you're not dealing with this. It could be that the data you have is not useful for answering the question, no matter what algorithm you apply. And having applied the algorithm, what can I learn from the data? can I infer what I want to infer? That, say, for example, the treatment being studied is useful or not? What action should I take as a result? Do I need to worry about bias, confounding, generalizability, concept drift? So this is sort of a sales pitch, but a reminder that I think statistical concepts and training are essential. So I guess I'm saying this to people, if you're thinking about if you're working in data science and you haven't had much statistical training, take the time to do it. Because statistical concepts like bias, confounding, generalizability, randomization, they're really, really important, and they're never going to go away. I can guarantee you that in 50 years, as science progresses, these kinds of concepts are going to still be important. How we deal with them might be different, but they're not going to go away. These really have a great shelf life. So statistical concepts and training are essential, and they're a central part of data science, however you work. Some important points. To me, and this is an important one, models should be kept as simple as possible, as they're easier to understand. Because then we can also anticipate when they're going to break. If you have a very complicated model that does something, it may make a decision in a health area, it's deciding what treatment to apply to patients, and then it stops working. If it's a very complicated model, it's really hard to know how to fix it, right? Because it's hard to know what went wrong. So simplicity really has its virtues, both because they're easier to make things easier to understand. It also makes it, again, easier to know when it's going to break and how to fix it. And Brad Uffron has a recent paper that's appeared, it's about to appear in JASA, that is on this topic. And there's discussion, and there's also discussion by Trevor Hasty, Jerry Freeman, and myself to that paper. A very interesting paper, and this is one of the themes. Quantifying uncertainty is really important, right? It's not enough to make a prediction, but you have to tell the user, this is how certain I am about my prediction, right? My prediction is it plus or minus 1% or plus or minus 20%? That's a big, big difference, right? And this is an important way to build trust in our models, right? Algorithms should be fair. There's a lot of discussion in the US now about this topic, and I'm not really working in this area myself, but it's an important area. Whoops. Here's an example that I've still working on with the students of an unsolved problem. I work a lot in proteomics. Actually, I work with a professor from Austin, Livia Eberlin, who is she's actually from Sao Paulo. She's a Brazilian working in the professor in Austin. She and I have worked together for about 8 or 10 years. She's a chemist. And one of the problems we work on together is high dimensional classification from proteomics. And one of the problems we have basically a classifier classifying normal versus cancer from features which are maybe 1,000 dimensional or 10,000 dimensional. And a classifier works very well. We've continued to develop it, and it's used for many cancers in Livia's lab. But one of the problems that we encountered was that the classifier, sometimes we get a query sample we're predicting in the future, and sometimes the query sample is so different from the training sample, we don't want to make any prediction. We want to abstain, right? We don't want to extrapolate. Like suppose we have a system that's looking at cancer samples from patients. It works well in training and validation, and then it's used in the future, and now a sample comes in that's so different than the training sample that we're forced to extrapolate. Now, what does that mean? In 10,000 dimensions, that means that the feature vector is far away in 10,000 dimensional space. Very big space, right? Well, trying to figure out how to get a classifier to abstain and say, I'm not willing to make a prediction. That's a really important and difficult problem. But it's a really central problem for the use of classifiers in high dimensional data, with high dimensional data in the health area. Because if you want something to be reliable, you want it to be able to say, sometimes I abstain. I'm not willing to make a prediction. And this may seem easy, but it's surprisingly difficult to actually come up with a system to do this in a reliable way, to abstain in a way that's quantifiably useful. So here's an example to me of an important problem that's unsolved. And it's also an example of why it's so good to work in applications. If I wasn't working with Livia, I wouldn't have even thought of this problem. But this just came up in the course of our work, and I realized that it's an unsolved problem that needs work. So another problem that's come up that's a very hot area around in statistics and data science is heterogeneous treatment effects for personalized medicine. In other words, given a patient, we want to figure out which of two treatments to give that patient, but typically from a clinical trial or an observational study, the patient's only got one treatment, not the other. So that brings up another interesting problem. How do you do cross-validation in this situation? Because it's a case where you don't get to see one of the outcomes, right? In use of supervised learning, you have observations and you have the outcome, and you can do cross-validation. In this situation, each patient's only given one of the two treatments, say, so cross-validation is really very difficult. So the point of this is some very basic but important problems that come up in these areas which need solutions. So I don't want you to go away thinking, gee, these smart statisticians have solved all the problems. That's far from the case. There's a lot of interesting, important work to do still. This is just a slide sort of on the generic supervised learning problem, which I'm sure you're all familiar with. We've got your trained data consisting of features or inputs, and you're trying to predict something like a phenotype or survival time or cancer versus normal. You apply a learning algorithm like the lasso, which I'll talk about in a moment, or boosting, or whatever your favorite algorithm is, and you apply it then to new data to produce predictions. All right, this is supervised learning. And what's sort of the general picture here? Well, in the old days, these data sets were small, right? Like in the 60s and 70s, you might have a small data and maybe 10 features, which those 10 features were sort of called by people who work in the area for many years, and they were the ones that were used. Nowadays, of course, it's a big change. Our data sets are much bigger. There's typically hundreds or thousands of features here, most of which probably aren't useful, but we need a learning algorithm to sort their way through the inputs and find the ones that are most important. In other words, we need to do feature selection. And this is a sort of schematic of, this is sort of the way that we like to sort of divide things. There's wide data where the number of observations is quite a bit less than the number of features. And for that, the lasso and elastic net are especially useful because they do variable selection. Whereas tall data, where there's many, many observations and fewer features, random forest and gradient boosting are typically useful. The lasso, of course, is something that I work on a lot and still continue to use very often, is basically least squares regression with an L1 constraint, right? This budget on the absolute values. And the nice thing about this is it's convex, so it's very computable, and it gives you sparsity. In other words, it does variable selection. It sets some of the coefficients to 0 if the bound is small enough. GlimNet, which I hope you've heard of, is a package that we being Friedman, Hastie, Noah, Sai, and myself, continue to develop. And it's used worldwide. I happily say it's had almost 2 million downloads, check recently. Actually, this is actually old now. There's a version 4. Version 3 just out about a few months ago. Features the relaxed lasso and other goodies like a progress bar. Version 4 actually, which is out about less than a month ago, it's all on CRAN, allows you to build your own family and deviance. Like for example, if you want to fit a lasso model to a negative binomial model, that wasn't possible for this. Now you can define for arbitrarily families and link functions, you can build them into GlimNet. So that's in GlimNet 4. So I suggest if you're interested in GlimNet, have a look on CRAN. Trevor Hastie has done a very nice job of this and has a very more general version of GlimNet that's ready for use. So the elephant in the room is deep learning, right? And the question is, well, will the lasso be eaten by deep learning, or and will other models be? Is it all we need? Like, why am I still talking about the lasso? Maybe deep learning is all we need. Well, first of all, what is deep learning? For those of you who may not have seen it, it's basically a reincarnation of neural networks. So deep learning is a model which has the inputs in a network configuration. The inputs are put through linear combinations to hidden units, and they're then passed through a nonlinear filter, and together as a combination they predict the output. So it's a nonlinear set of functions applied to a set of linear transformations of the input. A very general, kind of powerful model. This is a single hidden layer neural network. A deep net, which is the latest thing, has more than one such layer here. Might have up to 50 or 100 layers, each one passing the signal, the response to the next layer. and then eventually you get to the output. So what's changed? Like, why all the craze about deep nets, right? Neural nets have been around since the mid 80s. Well, I think the reason what's really changed in the last 10 years is that one big thing is the training sets are much bigger. So there's a lot more data, and neural nets can exploit that. And the computation is faster, right? This kind of network with multiple layers, you couldn't even do the computation 10 years ago. And now with GPUs and clever algorithms, you can do the computation. There's very nice software now in R and Python and etc. There's a lot of clever engineering ideas, convolution filters, stochastic gradient descent, etc., that have made them work well. They're deep. This deep thing is a relatively new. There's multiple layers now, typically. Whoops. Yeah. This is a single layer, but typically now there's multiple layers. So this is an interesting sort of side story, but Tommy Poggio of MIT gave a talk at Stanford a couple of years ago at a seminar on deep nets. And he said, it was interesting, he said, you know, in the 80s, people proved theorems to show that a single hidden layer neural network like this can approximate a smooth function arbitrarily well. If you take enough of these blue circles here, and this function is smooth enough, you can approximate it arbitrarily well. And the theorems were true, but what happened was, according to Tommy, is that people took the theorem very seriously and said, basically, we only need one hidden layer. The mathematicians have told us we only need one layer. We don't need to try multiple layers. And according to Tommy, that set the field back for 30 years because people didn't think about hidden multiple deep nets because the math said you didn't need it. Well, that was turned out to be a big mistake because, you know, theorems basically tell you something about a very idealized situation. In fact, people have found that deep nets, are extremely useful. Like putting multiple layers, although it's hard to mathematically establish why that's true, are extremely effective in practice. So it's interesting, and it's also a confession. I'm a Canadian. I was at Toronto in the early part of my career, a colleague of Jeff Hinton, and Jeff actually won the Turing Prize last year along with other people, for neural networks. Big, big award. I was a colleague of Jeff. I was actually working in his neural network group for years, and I didn't appreciate the potential of them at all. I thought, these guys are crazy. They're fitting all these models to thousands of parameters. I had no idea that they were useful, and I completely missed that boat. But I guess I'm not the only one. But I certainly was wrong, and now they're extremely useful for the reasons I think I mentioned here. That the data sets are larger, and the algorithms are much better. And people have realized that the deep part is very useful, having a deep net. So what does all that mean? Does that mean that we can just forget about the lasso and every other statistical model? But not at all. I think the important thing to note is that they're especially powerful when the features have some spatial organization or temporal, and the signal to noise ratio is high. So when are they good? You know, you see these problems where you have a large set of photographs, and you want to say discriminate between cats and dogs, right? Neural nets are very good at that. Why is that? Well, you have large data sets. The signal is very, very strong, right? A cat from a dog, a human can very easily tell the difference. The information, so the signal is very strong, and the information is spatial, right? Like you look at an image, you look at sort of for a dog, you might look at the ears of the dog, or for the cat, the whiskers. So there's information in the image that can be exploited by a neural network. Spatial information can be exploited by, let's say, a convolution filter. So that's a situation that's really tailor-made for deep nets. But they're not a good approach when the number of observations is pretty small. There's a large number of features, and especially if the signal-to-noise ratio is low, right? A lot of problems in medicine, in genetics and genomics, the signal is very weak, right? You're trying to figure out which genes predispose someone to getting cancer. The signal is very, very weak typically, right? It's not like we're going to find one gene and that gene's going to be, if that gene has form A, the person's going to get breast cancer. More likely that gene will give you more, say, a 5% higher chance of getting breast cancer. So when the signal-to-noise ratio is low, which is often the case in the health area, others have found deep nets are not as useful. I mean, you can certainly try them, but you'll find typically that they're not as useful in that situation. And as a matter of fact, Well, if also, if you want to interpret the model, a deep net is very hard to interpret, right? This model is complicated, right? You fit this model and then your collaborator, your medical collaborator says, explain to me how it works. It's a messy thing, right? It's got all these links and linear combinations. It's a messy function. So interpretation is difficult. Matter of fact, I've looked for examples where deep nets beat the lasso or boosting when the SNR is low, and it's hard to find such examples. So they have their role. They're very, very powerful, but they're not the best in every situation. So in general, you should always try these different tools in your favorite language, like R or Python, and see how well they work. But don't presuppose that one method or another is going to work the best, because it's not the case. So just near the end of my general comment section, some general advice. This is a cartoon of my experience, in talking to a postdoc, or sometimes I talk to people in companies. Have you tried method X? Have you tried boosting on your problem? Well, I tried that last year, it didn't work very well. And then you ask, well, what do you mean? What exactly did you try? How did you measure performance? I can't remember. Right? So this is a typical experience, right? People try things, it's sort of anecdotal. Well, the point is that details matter, right? So you should try more than one method, like the ones I've listed, for example, deep nets, the lasso, boosting. Use cross-validation to compare them and do it systematically. Keep scripts of what you did carefully. And your work should be reproducible by you and other people even years from now, because the details really matter. So keep track of the details so that when you go back to things in a few months, you know exactly what you did and you know how to improve it. Really important. And finally, in the last part of the philosophy section is, again, in praise of simplicity. And a nice quote by Da Vinci. And this is an experience I've had quite often. Like, I'll be asked to review a data analysis by a postdoc in biology or a company employee. Almost every time they're complicated. Like, I hear a story, like I hear a half-hour story about, here, professor, let me show you what I did. I took the data and then I put it through this package, and then I did this transformation, and then I found this other package, and then I did this, and then half an hour later, he or she shows me some beautiful color picture with arrows and colors, right? And they ask, so what do you think? And I tell them, well, typically I can't assess it. It's so complicated. There's multiple steps. Each one is pretty justified. It's hard to assess when people make a series of choices, just what you're getting at the end. Like, what's the type 1 error we're seeing, for example? And this happens to me a lot, like both when I talk to people at universities and companies, and I thought, why is that? And I think it's sort of a psychological thing. We're all, I don't know, some of you are like, as well, you have advanced degrees, some of you have PhDs or master's degrees. And the temptation when you have an advanced degree is that you're an advanced person. You want to complicate, you want to apply something complicated because, after all, you have a PhD, right? And then there's also the new problem. Everyone wants to hit everything with deep learning. And so our temptation as an advanced person is to apply an advanced method. But in fact, you should be more proud of something that's simple, right? So you should always try something simple first. And if simple is good enough, stop there, right? And don't feel guilty that, gee, I just did a plot and a regression and I'm done. You should be happy, right? I think that, again, we all sort of feel that because we have advanced degrees, we should apply something complicated. That's not the way to think about it. Only use complex things when needed. Try simple first. And if simple is good enough, be happy and be proud of it because it'll be more useful to someone. Simple doesn't always work. Sometimes you need more complicated methods, but don't always think you have to go complicated. Think simple and try to stay simple. And only move on to complicated if need be. So that may sound funny from someone who's come up with a lot of complicated methods in my career, but this is my practical advice. A lot of times you don't need those methods. Okay, so this is the end of my sort of philosophy overview section. And the last part is about this COVID-19 forecasting, but now it's a good place to stop and ask for any general questions about what I've said or comments.
Perfect. Thank you very much for part 1.
Yeah.
Guys, if you have questions, please shoot the questions through the chat. if you want to ask in Portuguese, we can work on translation as well. Let's go ahead. Some questions.
Or if you don't agree with me, if you think that once you always apply deep nets in any problem, I'm happy to.
We agree.
So there is a question there. What are the skills you'd say that a data scientist needs to have in order of priority?
Well, data or priority. Of course, it depends where you're working. Of course, you know, software skills are right up there. I mean, you need to be able to program in R, Python, and not only that, you need to be, you know, you have to be, have good programming skills and practices, organized code. And I can't, myself, I'm still working on the organized part. I do a lot of coding myself, but not always the most organized. So I would say definitely software skills, as well as statistical concepts, like I mentioned. Understanding the roles of randomization and bias and confounding and overfitting. So having some courses in statistics that go over those things, those are really, really important. I think those things are the foundation for all data science work. Software and statistical concepts, I'd say.
Perfect. Do you agree, by the way, that there is this necessity as well on the connection of these 2 bits with an application, in the sense of a data scientist is that guy that has these 2 skills plus the business understanding of what is going on?
Oh, sure. Yeah. I guess that's a good point. A data scientist has to basically will work in some area with other scientists or engineers or some application area. So having some understanding of those areas, and also being able to communicate your ideas, what you're doing to your collaborators is really important, because your collaborators often have much more quantitative even idea of the problem than you do, right? So communications in both directions is really important. Yeah.
Perfect. So there is another question from Windenberg Nobre about heterogeneous treatment effect. Yes. Why would cross-validation be useful?
Well, so that was to do with, okay. Well, because cross-validation be useful because, like in any situation, you have a model with tuning parameters. Suppose you're fitting a boosting model to predict heterogeneous treatment effect, or the lasso. It has tuning parameters, right? And those tuning parameters determine whether you overfit or not. So you need, just like in any application of supervised learning, you want to tune your model to avoid overfitting. Same thing here. So if you're using the lasso or say a boosting model in this context, you need to know how do I tune it to avoid overfitting, and that's where cross-validation comes in. So that's why. Yeah.
What would you say? So there is a question from Gabriel Franco. What would you say about the role of the statistician in the new world of data science and artificial intelligence?
The role. I mean, that's a general question. I mean, certainly, it's a very important role. There's a bit of a cultural challenge in that people in artificial intelligence tend to be better at PR, public relations. So yeah. They often do statistical things and they call them AI. So one of the things that statisticians, one of the challenges is getting ourselves heard, getting our points across and getting people to know that statistics is an important part of data science. But I mean, the role is a central one, to answer the question. And for the reason I mentioned, the concepts of statistics are central to data science. And I think one of the roles we can play is not only doing good data science, but helping to teach other people in data science these important concepts. Like many times I've seen talks in machine learning talks where, again, they take some data from a hospital and they run boosting on it, and then the results are, they present results which are all wrong because they haven't thought about things like the fact that the sample in the first place was biased in the way it was selected, that there's confounding, right? you can't finesse these central questions by applying a fancy algorithm, right?
Mm-hmm.
So again, I reemphasize statistics is central to data science, and the concepts of that of our subject are really important.
Let's see.
Yeah.
Andersonara is pointing to around the problem regarding deep neural nets and lasso. How can we understand SVM, support vector machines? It was introduced by Vapnik's statistical learning theory.
Oh, so yeah, I mean, I talk about support vector machines in various courses. Support vector machines are, they are kind of, they're closer to the lasso, I'd say, in the sense, well, in their basic form, they're similar to the lasso in the sense that they use linear combinations of features. The kernel support vector machines are more general. But I guess I'd probably say that support vector machines are somewhat out of favor now. I don't find cases where, basically, if I have the lasso, boosting, random forest, and deep nets, I think I've pretty much covered what I need to cover. Support vector machines can be useful, but I don't think there are many examples left where they are the best method. I don't have a systematic review of that, but I think they're a good method, but I think they somewhat have been subsumed by the other techniques. I think that's my current feeling.
Yeah.
It's not something I use very often anymore.
There is Ronaldo with a provoking questions. What would be the training for the statisticians in order to compete fairly with computer scientists that are using and renaming some of the statistical procedures?
So the question was, what is the training to compete with computer scientists? Yes.
Yeah.
In order to, that are using.
Exactly, and these computer scientists are pretty much reusing statistical methods and renaming them.
Yeah, that's very true. What training? Well, you know, I'm not sure I wanted to compete with that. That's not a very. I think. I mean, one thing we have, the computer scientists, there's more of them than there are statisticians. So we're outnumbered. I mean, what would we try to do, Trevor Hasty, myself, and others, we try to write books which are accessible that reach a broader audience. So one way is to work on communication, right? To try to write papers and books and give courses, YouTube videos that make statistics more broadly known. I think that's the best way to compete. You know, we have a good thing here. We have to get the word out. And as the questioner is saying, sometimes computer scientists are much better at getting the word out. And they might take something they're doing, they rename it, and then they get credit for it. So what's the solution? Keep producing good ideas and spend time communicating them, producing good software. And I'll get to that point later in this talk about the importance of producing good software, because that's the place where your methods get used and known when they're software. So maybe it's a good place to move on to the next section. Is that good, do you think? Or
yes, I think it's good enough.
So the last section is, you wanted to hear about COVID. So that's actually something I've been, let me just go full screen again. So again, this whole talk I'll give to you, I'll email to you, Benelton, and everyone can have a look at it. But so I'm skipping the middle section, and now this last section about COVID. So the last 3 months or so, I've been working with people at Carnegie Mellon, notably my son Ryan, who you may have heard of, was also a statistician, and Roni Rosenfeld, chair of machine learning there, and Ryan have run the Delphi flu prediction team at Carnegie Mellon for about 5 years. For about 5 years, they've been running this team that is doing forecasts for the CDC in the United States, forecasts of seasonal flu. And they've actually done very well. There's a competition every year among about 30 teams from around the US that tries to predict how much seasonal flu will come in the next few weeks. And this team has done 3 of the last 4 years, they finished first. So they're very good at this. And they got a center of excellence recently, along with the University of Massachusetts from the CDC. But then COVID arrived, and the CDC asked Delphi and other groups to refocus now on COVID-19. So starting around March, Ryan and Roni put together a team of about 25 software engineers and statisticians to do COVID forecasting and COVID information. And this team, I've been on this team working hard for the last few months on this. Most of the people are at Carnegie Mellon University, that's in Pittsburgh, in the United States. And there's a few people from outside of Carnegie Mellon. And let me just show you, so actually I'll show you the map which we've produced, and then I'll come back to talking about the experience. Let me just sort of cut to the chase and show you what our main product is. I've got it bookmarked here. So this is called COVID-Cast. This is the Carnegie Mellon Delphi COVID map. So this is, of course, a map of the United States, and there's lots of goodies here. There's, well, you can look at information by county or state or metropolitan area. Let's do state. And there's information, there's various things you can find. These are visits to the doctor due to COVID, hospital admissions. They have a symptom survey, which my son Ryan actually negotiated with Facebook, which asks people, and it's got a huge number of people, something like 100,000 people a week are asked, do you have symptoms of COVID? And there's a few surveys from Facebook that gives information. The idea, we're trying to forecast hot areas of COVID before we see cases. So these surveys, if someone says, I'm feeling COVID symptoms, then it might be a few weeks before they actually show, have symptoms of COVID, if at all. So these symptoms are supposed to be, these surveys are early indicators of COVID. And we're actually the only ones who, this is a sort of, it's an agreement that Carnegie Mellon negotiated with Facebook, and it's unique to our map. But then what we do is we take this information and put it out on an API, so the whole world has all this data available. And then there's mobility data, search trends, etc. And then we have a combined signal, which I'll talk about actually in the talk, which says, for example, June 28th, where are things the worst in the US? And we see it looks like it's Texas and Arizona, Mississippi, etc. So this is the map with a lot of signals and a lot of information. This was a huge amount of work. And that's what we've been doing, me and a team of 25 people have been doing for the last few months. And this work continues. Let me tell you a bit about the background of this now. So, and again, the link, this is called COVID-Cast, if you want to look at this yourself. So let me go back to the talk and say a bit about a background. Okay, so where was I? I was here. Okay. So our work so far basically has been trying to display signals and symptom surveys on the map you've seen. And now we're in even a more difficult phase of trying to forecast the future. Basically, the concern in the US that in many counties, the hospitals will be overwhelmed by COVID cases. So we're trying to forecast for the CDC, for example, along with other groups, which counties may be in trouble in a few weeks because the COVID cases are heating up. There's a lot of symptoms of COVID, and how that might affect hospitalization. Here's the group, by the way. There's Ryan, my son. He was a student at Stanford in statistics, not of mine, and now he's a professor at Carnegie Mellon. Roni Rosenfeld is the head of the machine learning department. These two have worked together for many years, and they're the head of our group. And there's the 25 or so people in the Delphi group. I'm in there somewhere. Okay. So what have I learned as a statistician? It's been quite an experience, I'll tell you. And as I mentioned, one thing is we need good data. I guess that's one big lesson for me in this whole thing, that the importance of good data. Usually as a statistician, I don't know about you guys, someone comes to me with good data. Scientists from the Stanford Medical School, Rob, could you help me? I've got this data, could you analyze it? In fact, in this kind of situation, getting good data is really important. Like, where do you look for the data? What's the quality of the data? So Ryan, solved that somewhat by approaching not only Facebook, but Google and Amazon as well for surveys. And with some success with it. So they're supplying us with these symptom surveys that go into our model, and they're doing so on a daily basis. It's complicated though, because when you talk about health data, companies are worried about, in the US especially, about whether they're going to be hurting patients, right? And whether you're going to be exposing the privacy of patients. So there's a lot of legal maneuvering needed to get this to happen. And we have and hundreds of thousands actually per day of these surveys coming in. And here's an example of the Facebook survey. So this is the basic questions we ask about COVID symptoms. And Google asks a similar kind of question. Shortness of breath, difficulty breathing, fever. And from this, we try to infer the level of COVID symptoms in the community. And we have more than other data sources. There's a major health provider giving us real-time data on doctors' visits, hospital admissions, and ICU. Google Health Trends, and a diagnostic healthcare manufacturer. We have data coming from every direction. Surveys, health data, lab data, and we try to use that. Well, we first of all display that on a map, and now we're trying to use it to forecast. So the experience has actually been, to me, it's like being in a startup company, right? It's high pressure, there's time pressure. We're trying to get things out, the forecasts out, for example, and so the CDC can make use of them. Daily Zoom meetings, a lot of coding, GitHub. And I have no idea, like I see a map like that and I think, I don't know about you, but I have no idea how much work is involved actually in producing, like making sure the data is of high quality, processing it into signals, make sure the signals are robust, and then just the engineering to get a map like that up there where you can zoom and zoom out, zoom in, there's a lot of work involved. And the data is very complicated. It's at many resolutions, it's very noisy data. And I said we launched on a Thursday morning. This is the example of the experience being a start. Around 10 p.m., the entire site was broken the night before. We figured out that one person had changed a file name and broke the entire system. Fortunately, around 1 in the morning, we figured it out, but it's like, this is the kind of thing that happens in a startup company. So it's been quite an experience as a professor to be working in this environment. And there again is the URL. And here's an example of some of the things we're seeing. So we get these signals from various places, like the Facebook survey, Google Health Trends, Google surveys, doctor's visits. So you might have noticed on the map, there was a consensus combined signal. How do we do that? We basically compute a principal component. So we compute a correlation matrix like this. So this is the correlation of these 5 signals across for different counties. And here's the first principal component. And this is the consensus, the combined signal that we show on the map, some version of this. And you can see that they're quite correlated, which is good, right? I mean, you have more confidence when they're telling you the same thing. Like, looks like, for example, Google surveys and Facebook surveys are pretty highly correlated. If they weren't, you'd be worried, right? You'd be worried that maybe it's just noise. But so stepping back, what have I learned from this? And I'm continuing to work on this. A great appreciation for R. There's a lot of talk about Python, which is also a great language, but R has the advantage of having a community of users who all put out software that everyone can use. So R and R Markdown, GitHub, CRAN, tremendously useful, especially on projects like this. And LimNet, which is what our lab produces, has been a central product, a central thing we're using. But just a comment about this is just make a plug. It's really important to spend time making software. In this work, I've pulled down a lot of CRAN functions from the central repository. Of course, they're all in CRAN, so they work to some level, but there's a lot of stuff that's not very good. You start to use it and it breaks in 5 minutes, or the documentation isn't good. So in a project like ours, it's no longer useful, right? So it's really important to spend time on software. Make sure it's solid, make sure it's well documented, support it, right? I think one of the questions someone asked earlier was, again, how can we compete with computer scientists? Here's a way we can compete. Make good software that really is high quality. Like software for statisticians in the past has sort of been like a second class, you do it later after you write your paper. Well, I've learned you really should spend time making good software. It's a place where the rubber meets the road. That's where people, what you want them to use your ideas, that's where they use them, in the software. And if they go to your package and they download it and it doesn't work in the first few minutes, forget it, right? There's some other package they're going to try. So spend time making good software. It really, really is important. It's important for the user, it's important for you. So I just want to really emphasize that. It took me many years to learn this, and I'm still learning it, but it's, sometimes doing software debugging isn't fun, but it's really, really important. Can't emphasize it enough. So we're moving now on to It's a lot of stuff here. Moving on to forecasting now, which is really difficult. Trying to forecast 4 weeks from now, how much will Jones County have? How many COVID hospitalizations? Trying to predict that with a supervised learning model based on Facebook symptoms and other things we have. And we've been talking to people in public health departments in California, for example. They'd like our help. There's a website called COVID Act Now, which we're working with. So we have customers for our forecast, but we're working hard to make them useful. We want to make sure that they're as precise as possible and they have uncertainty measures. So that's my work on COVID and other people. And I'll throw these up here. I don't mind this self-plug because they're all free online. These are books you may know. And this is a recent book by Brad Efron and Trevor Hasty, a nice overview book. I also mentioned this book, which has been very popular. There's a new edition coming out, just finishing it now. It'll be out by the end of the year. It has a chapter on deep nets, also a chapter on false discovery rates, and a chapter on survival analysis. So by the end of the year, this will be available, and I hope you'll enjoy reading it. So that's it, and happy to take more questions.
Perfect. Thank you very much.
You're welcome.
Guys, again, let's go through the chat and then I'll forward the questions. And I've got a few ones already, Rob.
Yeah.
Let's go ahead. So Paulo raised a general and philosophical question, and his question was, what is your point of view about the discussions related to data science versus statistics? And one example he gives is that some people fear that calling ourselves data scientists might be actually assuming one to lose part of his or her identity. And some others say that data science and stats are different approaches, etc. Do you have any thoughts on that?
I'm not quite sure. I can say that, for example, there's been discussion that in our department at Stanford, should we include the name data science in our name? Like, right now it's a Department of Statistics. So there's been some discussion about Department of Statistics and data science. And we've actually currently not moved to that. We want to keep the name. So I guess I think it's important to embrace data science. I mean, there's two ways we can go, but statistician can say, one option is, we're not data scientists, we're much better than that, but you guys go do data science, we're statisticians. Sort of take the high horse kind of approach. That's a bad approach in my opinion. I'd rather join the data scientists, work with them, and I mean, in some sense, we are data scientists. I think of statistics as an important part of data science. We're not all of data science. For example, data scientists typically know a lot more about computation than we do, about parallel processing, about databases. So statisticians, I think, are a key component of data science. I think it's the most constructive thing is to join data scientists and work with them. And so I don't think it should be a competition, it should be a cooperation. I don't know if that's answering your question, but.
Yeah. Tatiana points that you and Professor Hasty named this area statistical learning.
Yeah.
So that said, it would be nice to hear you mentioning what would be the main differences actually between statistical learning and machine learning.
Yeah, well, I would say it's a good question. I mean, there's a lot of overlap. I would say the main differences are in the what's emphasized. Like machine learning people tend to think of their methods as a black box, an algorithm that's applied to data. They tend to focus on predictions, classifications, and they don't tend to worry so much about interpretations or uncertainty. Whereas statistical learning is more model-based, right? An algorithm is fitting a model with some objective function. We think more about the interpretation of the model, the assumptions, and how much confidence we have in the predictions. So statisticians worry more about uncertainty, and we work off models. Machine learning people tend to think of models as a black box, and they apply them to data to get predictions. So I mean, that's a simplified version, but I'd say that's the biggest distinction.
Let's see. There was one question that was sent to me in private, and I'll forward here, and it's actually about if you could say anything about experimental design within the scope of data science, especially optimal experimental design. Do you have any thoughts on that?
Not exactly an optimal design. I'd say experimental design is important and tends to be ignored by a lot of data scientists. Like, I mean, again, working in the Stanford Medical School, I'll often get data from some medical assay like microarrays or RNA-seq, where they have a small set of samples they've collected, and they haven't thought about the experimental design. Like, for example, they're trying to determine some phenotype difference, and there's a batch effect because they didn't assign the chips in random to different batches. So I think experimental design in general is important to know about, and it tends to be sort of overlooked by people in data science. Optimal design, I don't have, optimal design really is sort of, it's in a very ideal setting. Imagine it has uses, I just don't have them at the top of my head, but I would say experimental design concepts are really important in data science.
Yeah. So Luis Carvalho from Fundação Getúlio Vargas in Rio de Janeiro is actually pointing out that you're stressing the importance of keeping models and approach simple.
Yes.
Do you feel that there is a balance between simplicity of the model and the complexity of the problem?
Well, like complexity of the problem, I imagine you mean the complexity of the scientific problem that you're working on. Yeah.
Exactly.
Well, I mean, I'm not sure if there's a balance. I think what tends to happen is, like, almost every biological problem is complicated. There almost is no simple biological problem. But what tends to happen again is that people start with a complex biological problem, and then they, on top of that, layer a complex statistical method. And that's a very bad situation because it makes it very hard to figure out what's going on. So I think however complicated or simple your problem is, you should start with simple statistical methods. Now, it might be the case that more complicated statistical methods tend to work better for complicated biological problems. That may be the case. But you should always start with simple and move on to complex only when you need to. And if the complex method doesn't perform any better in your hands, then don't use it. Try it, but don't start with complicated. Start with simple, no matter what your problem is.
That's perfect. Guys, if we have more questions for Professor Tibshirani. Okay. We do have one. What do you think is more important these days for a young statistician? Theoretical research or more applied algorithm-oriented research, or maybe both?
Well, I mean, that's interesting. My bias is, I'm not a theoretician, so my bias is definitely towards practical research. There's definitely a role. Let me say, for mathematical work or theoretical work, there's sort of two kinds of theoretical. There's theoretical work that is sort of math because it's fun, right? And doesn't have a lot to say about actual applications. And that's okay, life should be fun. And if you like doing math, that's good. Go ahead. I'm not going to discourage you. But there is theoretical work that also, discovers properties that are useful for practice. And that's especially good, important theoretical work to me. So theory has its role. Especially theory that's applicable. And to me, my passion is doing applied work, because that's where I really get the satisfaction. So,
yeah. So Ana Vasquez is pointing to the meta of effects of false positives on forecasts. Mm-hmm. And she gives one example where a given test could have a given specificity. But her point is, reports from Google and Facebook surveys are likely to be less sensitive than lab tests. Mm-hmm. And she's wondering if you have considered how these can be factored out in predictions of outbreaks, and is this automatically accounted by the use of a supervised method?
So she said that symptom surveys are likely to be less predictive than a lab test.
Yes.
That's true, but on the other hand, symptom surveys are available much more broadly. Like, right, we can get symptoms, we have symptom surveys, you know, across all counties at 100,000 a day. For lab tests, we have them on much fewer counties and much smaller numbers. So it's not like, you know, yes, I'd rather have a perfect lab test than a survey, but the reality is that we get much more of surveys much more often, much more broadly. So they're both useful. And the supervised learning algorithm, when you train it, it basically figures that out, right? It tries to use them for prediction. If she's right that the lab test is definitely better, then in theory, it'll give higher weight to the lab test and give lower weight to the symptom survey. But what tends to happen is it gives some weight to both of them because they both have complementary information. Yeah.
So Professor Lozada Neto asks, there is a real need for the market in terms of data analysts, statisticians, mathematicians, computer scientists, with this diversified formation who would act effectively within this new world of data. Do you think these professionals would be replaced in the future by data scientists?
So the first part was about statisticians being needed, is that right? And then
yeah, several professionals being required on the market today. And do you think that many of them would be replaced by data scientists?
I mean, and so are those several professionals were statisticians, or who are they?
Including statisticians, but also data analysts, mathematicians, computer scientists.
Well, I mean, the question sort of the answer is no, because those people, statisticians especially, think of yourself as a data scientist. Like, we're not competing. We don't need to compete with data scientists. We can embrace it. I mean, think of data science as as more opportunity for all of us, right? Don't consider yourself a statistician versus a data scientist. Consider yourself both. Like, be proud to be a statistician, but also be proud to be a data scientist and all the opportunities that it brings. So it's not us versus them. It's a cooperation. Like, so, yeah.
Perfect. Professor Edibert Lopes asks, any clue about funding for statistics after the pandemic in the US?
Is there any clue about the direction it's going to go, is you're saying?
In terms of funding for statistics?
Very hard to tell, right? I mean, as you know, the budgets in the US are just in shambles. So, I mean, I think in the long term, when all this horrible stuff is over, you know, there'll be healthy funding, because I mean, there's such a need for data science and statistics. It's just in every area, every walk of life. But for the next year, for example, it's very hard to predict. But in the long term, I'm optimistic.
Perfect. All right, guys. Any other questions? João Setzer, what are the next directions for statistics as a field? For example, causal inference, conformal prediction.
I think causal inference is a really big one. There's a lot of activity around Stanford, for example. Causal inference is really of interest now in a lot of areas like health, of course, but also economics. There's companies like Uber, for example, is hiring people to do causal inference to figure out the effects of various policies, pricing policies. So causal inference is a really, really good area. I think what I tend to think of is I tend to look where the data is. Like, I think complicated data like now from surveys from Facebook or mobile phones, right? People now collect health data on mobile phones. It's very complicated, right? It's temporal, there's selection bias, but wherever there's interesting new data, there's going to be new problems. So it's hard to be a prophet, but if I was looking for where the important areas are, I would look for where the technology is going and the kind of problems that it's going to bring, because that's a good place a good hunch as to where the exciting problems are going to be.
Yeah. Perfect. Okay, I think we are a little bit past our time. It's been 1 hour and 10 pretty much. Professor Tibshirani, thank you very, very much for making the time to be with us today. I'm really, really excited that we got this opportunity. One last question, let me not let this pass. Actually, Paulo from Curitiba in the south of Brazil is asking, is statistics doing its job facing the pandemic so far? And if you think there is something missing, what is it?
Well, is it doing its job? I mean, there's been a lot of, let me put it this way, a lot of shoddy work done. What's happened in the US especially is a lot of people are working very quickly and producing papers and forecasts and making statements that are very poorly supported by data. So, and I've actually been involved in trying to fight some of this, both at Stanford and around the country. So I wouldn't necessarily blame statistics, but people are misusing statistics and doing sloppy work, and it's being advertised in the media and having a lot of effect on public policy. So I think it's statistics and science in general has not done a good job. In the US, of course, it's partly exacerbated by the fact that science has such a bad name, right? That our central government is also like, doesn't seem to rely on science. So it's a very difficult situation. I wouldn't blame statisticians, but there's a lot of bad statistical work being produced and being advertised. There's some good work too, but the bad work tends to get more press. So.
Yeah. And I seem to have missed another question by Professor Josemar Rodrigues. What do you think about the Bayesian methods within the scope of data science?
Oh, you guys are asking me the whole everything. Bayesian methods are useful. I don't tend to use them that much myself, but I think, and like any method, it has its place. And I think in many situations, for example, when you try to borrow strength across geographical areas where you have sparse data, empirical Bayes methods, for example, are very useful in those situations. So I think Bayesian methods are very useful. I always like things that are useful. So I don't think you should be a Bayesian statistician or a frequentist statistician. You should use whatever is useful. Don't be dogmatic about it. I mean, some Bayesian statisticians, they basically say it's either Bayes or the high, if either apply Bayes or nothing at all. Well, that's not reasonable to me. It's like, it's not reasonable to be a frequentist, only a frequentist. Statistics is a set of tools, and use whatever tools are useful and try to verify the usefulness on the data itself. So, you know, I don't do a lot of Bayesian stuff myself, but I have respect for it. It has its role.
Indeed. Rob, thank you very much for taking the time to be with us today.
You're welcome.
Very much appreciated.
I've never been to Brazil, so maybe someday when all this when the world's more in order, I'd love to come and visit. So
I'm pretty sure we can make that happen, and there are some key people here in this audience who can actually help us on making that dream coming true.
Great.
Thank you